Okay, last two examples on optimization. Example 4. A rectangle is bounded by the x and y axes. This rectangle, it's bounded by the x-axis and the y-axis. And the graph of this line with the negative slope, y equals 3 minus a half x. What length and width should the rectangle have so that its area is at a maximum? So we want to maximize area. Area is equal to x times y. Well, we're bounded by the x-axis, we're bounded by the y-axis, and we're bounded by this line, meaning that this vertex is always going to have the same point as any point on the line y equals 3 minus a half x. So this coordinate is x, comma, 3 minus 1/2 x. Meaning area is x times 3 minus 1/2 x. Distributing, area is equal to 3x minus 1/2 x squared. And so we got an equation that's going to represent this scenario, and we can take the derivative. A prime is 3 minus x. And we want to know when that's equal to 0. And that happens when x is equal to 3. And we can do a quick verify. Number line, a prime at 3, right? And so we plug in x equals to 0. We're going to have a positive value. So we plug in x equals to 4. We're going to have a negative value. So positive to negative, increasing to decreasing. This is definitely a maximum. This maximizes area because we change from positive to negative. So now we can find y. Y is equal to 3 minus 1/2 times 3. So y is equal to 3 minus 3 over 2, and that is equal to just 3 over 2. So to answer the question, dimensions that maximize area are x equals 3, y equals 2, 3 over 2. Cool. And then example number 5. Determine the point on this line, y equals 2x plus 3, so that the distance, this is what we're going to do, the distance between the line and the point is a minimum. The line and the point, 1, 2 is a minimum. So we want to optimize distance. And we want it to be a minimum. We want it to be as close as possible. Well, way back when, distance formula is x2 minus x1 squared, y2 minus y1 squared, holding under the square root, remember that? So distance is equal to, okay, well, on this line we'll have some x and y points, so it's going to be x minus 1 squared and y minus 2 squared, all under the square root, right? And right now we've got an equation in 2 variables, but conveniently for us, we know what y is equal to. So we can say that distance is equal to x minus 1 squared, and y is equal to 2x plus 3. So 2x plus 3 minus 2 squared, holding square rooted like that. And then, let's see, we can do a little simplifying. Distance equals x minus 1 squared and 2x plus 1 squared, all under a square root. And we can do our distributing. X squared minus 2x plus 1, 4x squared plus 4x plus 1, all under a square root. We can do some combining of like terms. 5x squared plus 2x plus 2, and this is all to a power of 1/2. That's pretty good. We can minimize that distance now because we're going to take the derivative. So the derivative is equal to 1/2 5x squared 2x plus 2 negative 1/2, and then chain rule 10x plus 2. So d prime 1/2, and this it's going to be 5x plus 1, and then this is the square root of 5x squared plus 2x plus 2, right? And we really want to know when d prime is equal to 0, and that's only impacted by the numerator when that's equal to 0, so that's going to be when x is equal to -1/5. That's when we've got this minimum value, or hopefully, we just see if the sign changes. So we check on a number line. D prime, -1/5. If we check anything less than that, we're gonna negative. We check anything bigger than that, we're gonna get a positive. So that means the distance goes from decreasing to increasing, making this absolutely a minimum value. So we had to determine the point. So distance is a minimum when x equals -1/5. This is a 5. And so all we need to do is plug this in here and just solve for y. So the point's going to be -1/5 for x, and for y it is 13/5. Those are your coordinates, -1/5 and +13/5.